Okay, we are now going to start talking about the discrete Fourier transform. And it's important to differentiate it from the discrete time Fourier transform. So it gets confusing, but after a while you get used to it. That Fourier transform which we studied earlier, the discrete time Fourier transform, you typically say DTFT, and this is discrete Fourier transform, which is DFT. So the first question I'm sure many of you are thinking is, why another transform? Didn't we already have enough transforms? And indeed, we have studied many transforms. You have done Laplace transform, continuous time Fourier transform, DTFT, Z transform. These are four of the major transforms that you have seen in your earlier classes. Now, all of these transforms are great for analytical purposes. But what we are now doing is digital signal processing. We are talking about processing inside digital systems, and none of these transforms are great for doing computations inside digital systems. And the reason for that is because all these transforms are functions of continuous variables. They might be transforms of discrete time sequences. For example, GTFT. It's a transform of a discrete time sequence. But the transform itself is a function of a continuous variable. So we say we have a transform, we have a sequence Gn, you compute its DTFT, you get G of e to the j little omega. Well, little omega takes all values, even if you stay between minus pi and pi, it takes all values between minus pi and pi. So little omega is a continuous variable. And if there is one thing we know about processing in digital systems is that we want to work with discrete quantities, not continuous quantities. So what we really want is a transform that, of course, is somehow related to some of these transforms, and we'll see that the discrete Fourier transform is very closely linked to the DTFT, but it also helps us do computations in a very efficient manner inside digital systems. So, and the other property that the discrete Fourier transform exploits is that all digital systems, so in our analysis we say, for example, we often write, okay, assume G of n equals to U of n. So a signal which stays one forever. But in reality, if we are storing things inside digital systems, our signals are always finite length. We don't have an infinite length sequence. Every computer has a finite amount of memory or finite amount of storage capacity. So all signals in digital systems are finite length. Okay, so then what is DFT? Now, if you go to a graduate class or a more advanced class, I will give you a more formal explanation of what a discrete Fourier transform is. But for the purposes of this undergraduate class, this is how I would describe it to you, which is that a DFT is a discrete finite length transform of a discrete finite length signal. So keep the DTFT in mind, and let's talk about how is what I just wrote, how is that different from DTFT. So a DTFT can be used to find the transform of a discrete finite length signal. That is common to both. But what is different is that DTFT is a continuous transform. It's a function of a continuous variable little omega. You write g of e to the j omega, little omega goes from minus infinity to infinity. Whereas DFT is itself a discrete transform. It's a function of a discrete variable. And whenever we talk about discrete variables, all we have to think about is sequences, values 0, 1, 2, 3. Right? And it is itself also finite length. Okay? And because of the fact that it is discrete itself and finite length, you can compute it in digital systems. So the two most common uses of DFT is, number one is approximation, and as we said, we'll see it later what is the relationship between DFT and DTFT. The fundamental use, or one of the uses, is approximation of the DTFT of discrete signals. And this is studied under the name of spectral analysis. Okay, spectrum for frequencies. So you get, for example, you have machines, spectrum analyzers, you have other things, you record a music, you want to find out what are the frequencies present in the music, you use DFT. You measure some radio frequency waves, and you want to figure out, for example, these days you get on your smartphones, you get apps which tell you which Wi-Fi bands are active and which Wi-Fi bands are not if you want to set the channel for your Wi-Fi router. That uses DFT. Radar, if you want to figure out where an aeroplane is, it uses DFT. So it is very widely used in a number of applications. The second purpose of DFT is it leads to faster processing of discrete time signals through the use of the relationship between DFT and linear convolution, which we'll study later. Okay. This is, in fact, one of the main sort of attractions of DFT is that you can compute it in a really, really fast manner. Okay. People who go on to do communications, you will learn about a technique called OFDM, orthogonal frequency division multiplexing, which is pretty much in any modern cell phone. It's a integral component of that, and it can't happen without DFT. If you did not have DFT, you won't have these fancy phones that could communicate with very high data rates. Okay, so DFT is really ubiquitous even if you don't realize it. In fact, your cell phone is doing that almost all the time, or at least modern cell phones are doing that almost all the time. So let's try to nail down some of the definitions or some of the terms that we have talked about so that we all understand their meaning in the same way. So the first thing is, what do we mean by, I wrote earlier, finite length signals. So what do we mean by length of a signal? Length of a discrete signal, say xn. So length of a signal, for the purposes of digital systems, we often say that it starts at n equal to 0. Because in a digital system, you are storing values, and without loss of generality, you can say that the first value is always n equal to 0. Right? Now, if you say the signal is starting at n equal to 0, so then the range of values of n beyond which xn is exactly 0 is called length of the signal. So in terms of examples, if I had xn equal to delta n, then I will say that the length of my signal is 1. Okay. I need to store only one value, because after that it's 0 all the time. So why should I waste my digital system's storage resources to store zeros? I just know it's 0 afterwards. So the length of my signal is 1. I could have xn equals to un minus un minus 4. So it goes from 0, 1, 2 up to 3. In that case, the length is 4. It's all ones for first 4 values, then it becomes 0 all the time. If I have xn, which is given by, let's say at 0, it is 1, then it is 0, and then it is some other value. Now, it is 0 in between, but I still have to store those zeros because I need to know where the zeros occurred within the signal. So even though I have zeros in here, I'll still call the length of this signal as 4. Okay. It's really about how much space I am devoting to store that signal in a digital system. For the purposes of DFT, that's how I'm going to define the length. So here is a final example. Xn equals to delta of n minus 3. So the length of this signal is still 4 using the convention that we talked about earlier. We say that the signal starts at n equal to 0. So delta n minus 3 means that you are storing 0, 0, 0, and 1. So you are still having to store 4 numbers. Okay. So in that case, I will call the length of this signal still 4. Now this is just the convention that I'm using, but that's how we'll store these things in digital systems. Okay. Now sometimes we will want to actually increase the length of the signal. So if I look at this signal, the first one, delta n, sometimes I would add zeros. So first of all, in real mathematical sense, saying that I add zeros at the end of the signal makes no sense. We know the signal is 0 after n equal to 0. But from a computational perspective, I can always store it as one number, 1, or I can store it as 1, 0, 0, or 1, 0, 0, 0, 0. I can add what is called zero padding. I can add more zeros to my signal at the end. By adding, I mean you literally store it in your computer. And we'll see that there is some value to increasing the length of your signal. Okay. It's important to realize that these discussions are in relation to how you store things. Even though we are still talking about signals, this is about how you store things. And that's why the meanings are a little different from mathematical meanings. Okay. So if I write xn equal to 1, 0, 0, 0, what I mean is that when you, for example, open up MATLAB, you are literally writing a vector with 1, 0, 0, 0. In that case, you have added 3 zeros at the end of your signal. By adding, I mean you have stored purposefully those extra zeros. Right? So this is called zero padding of a finite length signal. Okay. Strictly speaking, the length of the signal is still 1, but you have added 3 more zeros. Why would you want to do that? We'll look at it later. Okay. So that defines the meaning of length in relation to DFT. Okay. Because now our attention is completely going to computations, digital systems. So let's talk about now DFT. So again, as I said, if you go to higher levels, graduate classes or more advanced classes, some of these things are not technically rigorous. With that caveat in mind, let me just say that DFT is defined only for finite duration sequences. Okay? And we often write the length of the sequence as n. Okay? So you say, take a DFT of a length 1024 signal, or take a DFT of length 256 signal. Okay? So whereas DTFT, you can compute a DTFT of a unit step. DFT, we are going to focus only on DFT of signals that are finite duration. Why? Because in a computer, we are only going to store finite duration signals anyways. Okay. So that's the part of, that explains this part of what I called about DFT, that it's a transform of a discrete finite length signal. We defined length. We said DFT is defined only for finite length signals. Let's now talk about the second part. The DFT itself is discrete and finite length. What it means is that the output of DFT, it is itself a discrete sequence. So it's It's a discrete transform, so it's a function of discrete variable. We'll write it as capital X, and the index we will use is k of length at least as much as the length of the signal. So that's where this part comes, that DFT is itself a discrete transform. None of the other transforms that you have seen before are discrete transforms. They are transforms of discrete signals, but they are not discrete transforms. So compared to other transforms, now we have seen that actually DFT itself has a notion of length. So actually, we just don't say compute DFT of a signal. There is another parameter that we have to associate with DFT. DFT is always associated with some length, which describes the length of the transform. We previously talked about the length of the signal. We are now talking about the length of the transform. So, for example, the term that is used is n-point DFT of xn. Or you will hear that compute 1024-point DFT of a length, let's say 128 signal. Yeah? Because we said that the length of the DFT can be longer than the length of the signal. So it's not just enough saying compute DFT. Yeah? So having defined all these terms or these motivated this, let's talk about then when we talk about transform, our transform always has an analysis equation and the synthesis equation. The analysis equation is where you take the signal and take it to the transform domain. So the definition, mathematical definition of DFT or the analysis equation is as follows. So you say that, say, xn is of length n. Okay. So then you will compute a DFT of xn, which is going to be xk. So this is a length n signal, and right now I'll just say compute n-point DFT. So this is length n, and I'm computing xk, which also has length n. So what is the expression for DFT? It is x of k is summation n from 0 to n minus 1, x of n e to the minus j 2 pi k over capital N times little n. And this you evaluate for all values of k between 0 and n minus 1, where k is an integer. Okay. So this is the DFT formula. You start with a length n signal and you end up with a sequence which is also length n up to this point. So one thing to focus in this definition of the discrete Fourier transform is that I'm saying k runs from 0 to n minus 1, where k is an integer. Right? But if you look at the definition, actually, you see that you could actually plug in any value of k in this expression. This summation is still well defined for k naught in 0 to n minus 1. So what happens if you calculate actually the values of k which are beyond 0 to n minus 1? Actually what happens is it turns out that the DFT as a function of k is a periodic sequence with period capital N. Okay. What this means is that if you compute x of k, then that is equivalent to x of k mod n. Okay. So where this notation means k mod n. So just to remind you, if you don't know the formal definition of mod, k mod n is the smallest positive integer are such that the following holds. You can write k equals to n times another some integer. The integer can be positive or negative plus r. Okay. So if you translate that further, what it means is that if, first of all, if k is in the range 0 to n minus 1, then this means that k mod n equals to k. So if k is a number between 0 and n minus 1, you get back k. Okay. Now, the other possibilities are that if k does not belong to this range, so it is beyond this range, then there are two possibilities. Then, number one, if k is positive, then k mod n is simply equal to remainder of k divided by n. Okay. And if k is negative, then k mod n is n minus remainder of k divided by n. So what this means is that if you were to calculate, for example, if you were really to calculate, although for DFT, you will not need to, you should indeed focus on 0 to k minus 1, but it is still important to be familiar with this concept that the DFT is a periodic sequence in k, and this definition of mod will come back to it later in the definition of some other quantities in the context of DFT. So it's important to just note that. So if you were to, for example, calculate x minus 1, right, that is the same as x. So minus 1 is not in the range 0 to n minus 1. And let's say, so say n equal to 5. So that is minus 1 mod 5. Okay. And what this means is that if you look at this expression, right? So this is in this range, this is negative. So what will be x minus 1? So let's change the formula to n plus remainder of k divided by n, right? Or another version could be that n minus remainder of absolute value of k divided by n. So both will work. Okay. Okay. So if you use that formula, then it will be, if I just go with the second one, it will be 5 minus remainder of 1 divided by 5. So the remainder is 5. So it's 4. Okay. Similarly, if I were to compute x of 5, right, that is x of 5 mod 5, and that is remainder of 5 divided by 5, so the remainder is 0. So what I mean to say here is x5 minus 1 and x4 and x0. Okay. So this is periodic. Effectively what this is saying is you have, so if I have 0, 1, 2, 3, 4. So this is k, right? And for k equal to, so this is your main DFT sequence. Whatever the values are, I'm not writing the values right now. Now the sequence starts repeating itself. So at 5, it is actually going to be the same as x of 0, right? And similarly, at minus 1, it's going to be the same as x of 4. So it's a periodic sequence where it repeats itself after every 5 with a period of 5. What this is saying is that if you were to treat the DFT as an infinite sequence, you will find out that actually it's a periodic sequence. There, it has only n unique values. So even if we treat DFT as an infinite sequence, it has only n unique values, which go from x0 to x of n minus 1. And it repeats itself after that. Okay? And we haven't formally verified that, but it's easy to verify because if you plug in k here, which is above 0, which is not in the range 0 to n minus 1, because of the periodicity of complex exponentials, you will get back this periodic extension that we talked about. So not so much that will concern us right now, but when we talk about things like circular convolution and circular shift, this definition of mod in particular will appear there. Okay. So another thing that I want you to be aware of is that because writing e to the minus j 2 pi k over capital N can take a lot of time, people came up with this notation of Wn, which is e to the minus j 2 pi over n. Okay. So sometimes you will see the shorthand that the definition of DFT will be written as x of k summation n from 0 to n minus 1, x of n, w of n, kn. And again, we'll just focus on k from 0 to n minus 1. So this is your, as we talked about earlier, this is your analysis equation or the forward transform. Right? So what is the inverse of this transform? So if you are given, right now we have said is if you are given xn, you can go to the DFT xk using this formula. Now a transform by its very definition means that you don't lose any information. So you can go back and forth between the transform and the original sequence. So how do we go now from xk back to xn? How do we do that? And that, as the operation implies, we are synthesizing back our original signal. So that's called the synthesis equation or inverse transform or inverse DFT. So what is that expression? So that expression is now in DTFT, right? DTFT is a transform of a discrete sequence, but DTFT is itself continuous. So when you write the inverse DTFT formula, you involve integration in that. Now DFT, as we talked about at the start, is a discrete transform itself. It's a transform of a discrete sequence, but it's a discrete transform itself. And so because of that reason, your inverse DFT formula will actually still involve summations. So the formula is given by 1 over n summation k from 0 to n minus 1 x of k wn minus kn, or where wn minus kn means simply e to the j 2 pi kn over capital N. Right? And n equal to 0, 1 up to n minus 1. Okay. So this is the inverse DFT formula. And the things to keep in mind here too are that n goes from 0 to n minus 1. So this capital N, the number, is a function of how many points of DFT you took. So if you took, let's say, 10-point DFT going from xn to xk, you should use the same 10-point, right? Where point means this capital N, you should use the same capital N. Okay, because if you really use this formula just like the DFT formula, if you plug in little n different than in the range 0 to n minus 1, this formula will still be valid. And what you will get back is just like the previous case, you will get back a periodic sequence. Now, why does that periodicity come back? So is not something that we will go into, but just want to mention that interestingly, xn remains defined for n, just like the DFT case, n not in 0 up to n minus 1. And as you may guess, if n is not in this range, then in that case, xn can be written as x n mod k, mod n. Which means that if you were to compute xn for values beyond 0 to n minus 1, you will get back a periodic sequence which repeats itself after every n periods. But from the practical perspective, you will only care about this range, 0 to n minus 1. Yeah? Now this formula should make it clear to you one of the advantages of DFT, because both the DFT, the forward DFT formula and the inverse DFT formula, since they only involve summations, first of all, the summations are finite. You are only summing n things. Right? And secondly, even in the inverse DFT, you only have a summation, which means that these things can be computed inside a microprocessor, a digital system. So that's where what we talked about earlier, the power of DFT comes in, that unlike all the other methods, all the other transforms that we have studied, which have to be approximated in digital systems, DFT can be exactly computed in DSP systems. So let's do a couple of examples to help us understand how DSP works. So the first example is we are given xn equals to delta of n. And this means that length of xn, if I write it like this, the length of xn is equal is 1. And now we are asked to compute its DFT, x of k. Now, the main thing here to ask here is, what is the length of my DFT that I want to compute? So if I want to compute DFT of xn as it is given right now, and what I mean by given is how it is really stored in a digital system, then I am stuck with using a one-point DFT. But oftentimes what you would want to do is we want to compute n-point DFT where n is much bigger than the length of the signal, than the original length of the signal. So, for example, say n equals to 64. I want to compute 64-point DFT of xn. So what do I do in that case? We talked about it earlier, that a superficial way of increasing the length of the signal, again from the perspective of how things are stored in a digital system. If it's xn equal to delta n, you only need to store one number. But what you can do in digital systems is that you can artificially inflate the length of the signal by doing what we talked about earlier, zero padding, which means that we define our xn, and by define, I mean I'm not changing the sequence, but how it is stored in my digital system, I'll store it now as 64 numbers. I'll store n equal to 0, I have 1, and then I'll store 63 more zeros. Notice that the signal has not changed. Zero padding does not change the mathematical definition of the signal. But from the perspective of DFT, the signal has essentially changed. Okay? If you use a different n, you are going to get a different DFT sequence. First of all, n defines the length of your DFT sequence. So if you have n equal to 12, your DFT sequence is 12 length. If your n is 64, your DFT sequence is 64 length. So very important point to keep in mind. So once we describe, doesn't matter what the length, original length of my sequence is, once we decide that I'm going to compute n-point DFT, where n can be any number bigger than or equal to the length of my original signal, then we can compute the DFT using the DFT formula. So let's go by that. Now that we have zero padded our sequence, I have xk. It is summation n from 0 to n minus 1. So it's n from 0 to 63. I have xn e to the minus j 2 pi k over n times little n. Now I plug in the values of xn. Of course, everything is, all xn's are 0 except xn equal to n equal to 0. So I will get 1 times e to the minus j 2 pi k over 64 times 0 plus 0 times e to the minus j 2 pi k over 64 times 1 plus everything else will be 0. J 2 pi k over 64 times 63. So xn is 0 for the remainder 63 value. So this whole summation is going to be 0, and this thing is e to the 0, so that's 1. So I have that x of k equal to 1 for k between 0 and n minus 1, or where n minus 1 is 63, so let's put in that value. In general, you could also compute the same thing for capital N any number. We still get the same formula, x of k equal to 1 for k between 0 and n minus 1. So if I plot my x of k, if I plot my DFT, which is a sequence, I get for k equal to 0, I get 1. For k equal to 1, I get 1. And up to k equal to n minus 1, I get 1. Okay. So I don't want to go beyond the n minus 1 limit. So very simple to compute DFT using the expression. Right? And in a computer, of course, it's just a summation. You just fire up MATLAB and you write the summation. Very simple. So then let's look at whether the inverse DFT formula works or not. Right? So you are given, let's say you are now given this DFT expression for some capital N. And you are asked what is the original sequence that this DFT belongs to. So you use the inverse DFT formula to figure that out. You say xn equals to 1 over n summation k from 0 to n minus 1 x of k e to the j 2 pi k over capital N times little n. Okay. By the way, if you notice the DFT formula and the inverse DFT formula, you will realize that the main difference is that there is a factor of 1 over n in the inverse DFT. And other than that, they are pretty similar, except that the usual thing that if the complex exponential here has the negative sign, then the other one has the positive sign, and so forth. Okay, so in this case, what do we do? So let's plug in the value of x of k. It is all 1. So we get 1 over n summation k from 0 to n minus 1 e to the j 2 pi little n over capital N times k. Okay. Now what do we do? So this sum is a geometric sum, and if it doesn't strike you, it might be best to write it in the form of that shorthand notation. So remember that Wn was defined as e to the minus j 2 pi over n. So this sum I can write as 1 over n. So this is of course a perfectly valid comp number, right? So this sum can be written as k from 0 to n minus 1 w of n times little n raised to the power k. Okay. So this is like r in your geometric sum. Your geometric sum is given by summation, let's say k from 0 to n minus 1 r to the k, right? As long that formula is given by it's r to the n 1 minus r so this is incorrect. It's 1 minus r to the n over 1 minus r, right? Now this is your geometric sum formula. This formula of course is valid as long as r is not equal to, so this is valid as long as r is not equal to 1, because if r is equal to 1, then you will get 1 minus 1, which is 0, divided by 1 minus 1, which is 0, which is 0 divided by 0, that's undefined. So we have to make sure we'll compute this geometric sum while being aware of the fact that our r to the n must not be, or r must not be equal to 1. So we are defining our r in our case is equal to wn to the little n. This means that for n equal to 0, r is equal to 1. Right? If I put in n equal to 0, wn to raised to the power 0, that's 1. So we have to use different cases for r equal to 1, for n equal to 0 and n not equal to 0. So for xn, for n equal to 0, we'll have to just use the sum as it is. For n equal to 0, it will be 1 over n summation k from 0 to n minus 1. And that will be 1 raised to the power k. It doesn't matter what the power is. We get n divided by n, which is equal to 1. Okay. Now for n not equal to 0, and we still have to be careful, but it turns out for any other value, for n not equal to 0 and up to n equal to n minus 1, indeed r is not equal to 1. Right? So in that case, I can use the geometric sum and I get xn equal to 1 over n. The geometric sum is 1 minus wn little n n over 1 minus Wn little n. So what is Wn n times capital N? That's e to the minus j 2 pi. This is actually, because of the definition, this should be minus here, but none of the results change. Minus here, minus here, minus here. So this will be e to the j 2 pi over n times little n times capital N. So this gets cancelled, so it's e to the j 2 pi n. What is e to the j 2 pi n for n not equal to 0? It's 1. If you don't know why, just look at cosine of 2 pi n plus j sine of 2 pi n. Right? Sine of 2 pi n is always 0 and cosine of 2 pi n is always 1. So this is equal to 1. So I plug in 1 here. I get 1 minus 1, which is 0, but the denominator is not equal to 0, so it's a valid division by, so I get xn for n not equal to 0 is equal to is given by 0. So my final answer is then xn equal to 1 for n equal to 0 and 0 for n not equal to 0, which is xn equal to delta n. So indeed we get back what we started with. Now that's a trick that you will actually see it again and again in your DFT calculations, which is the geometric sum. Because of the nature of the DFT and inverse DFT, geometric sum actually keeps on appearing. And some of the most common mistakes that I have seen are students not being careful about this, using the geometric sum, but not being careful about 0 divided by 0 case. Okay. Other than that, it's plain geometric sum. Nothing fancy about it. You could extend this example to the case where you say xn equals to, let's say, delta of n minus m for some m between 0 and n minus 1. So, for example, for m equal to 1, you have n equal to 0 is 0, and n equal to 1, you have 1, and then it stays 0 till n minus 1. Okay? And if you compute the DFT in that case, just like the previous case, it's very trivial. The answer comes up. All the terms in the sum will be 0 except 1. Which term will be non-zero? It will be Wn km. 0 is less than or equal to k, less than or equal to n minus 1. So if you compare to the previous case, in the previous case, your DFT was all 1. In this case, your DFT is a complex number. So to understand that, we can look at the magnitude, and the magnitude of this is, of course, 1. Right? So in magnitude, a shifted delta and a delta, they have the same DFT. Okay? But what will be the difference if I look at the phase of x of k? Right? So that's phase of e to the j minus 2 pi over n km, and that phase is simply 2 pi km over capital N. Right? So you do have a phase shift in your sequence, in your DFT, which sort of gives you the sense that, oh, this is something similar to what we have seen, right? we took a delta function and we shifted it, and what we are getting is the same magnitude, but there is a phase shift in my DFT sequence. We'll come to that later. Why does this happen? Okay. Let's take a look at another example. So this is example, I believe, 5.2 in your text. Now this is xn equals to cosine of 2 pi r over n times little n, where r is an integer between 0 and n minus 1. Okay. And you are asked to compute its DFT. Now, if I am asked to compute its DFT, there is an important point that I am missing in this formulation. I'm saying my xn is a cosine. Right? It's a cosine with frequency is 2 pi r over n. Okay, so that's fine. It's a periodic cosine because of the fact that the frequency can be written as a rational multiple of pi, right? So it's a periodic cosine. But there is one factor that I need for me to be able to compute its DFT. So the way we have defined this sequence currently, this is an infinite sequence. It goes from minus infinity to infinity. And so according to the DFT formula that we have looked at, we need the sequence to be finite. Okay? In this case, I'm going to define the sequence to be a length capital N, which means that this is a sequence, this is effectively a cosine, but only over one period. Okay, I'm not looking at cosine from minus infinity to infinity because I'm trying to do DFT. So this is a cosine of frequency, the way I have defined it, 2 pi r over n, which means it is periodic, right? But over only one period. Now, so how will we compute the DFT? Let's say that we want to compute endpoint DFT, the same as the length of the period. So endpoint DFT x of k. To compute that, because of the nature of DFT formula, it's always preferable to express your sequences in the complex exponential form. So we'll first write, using the Euler's identity, we'll first write this cosine in terms of complex exponential. So it's 1/2 e to the j 2 pi r over n times n plus e to the minus j 2 pi r over capital N times little n. Okay. So I'll just use the shorthand notation. It's Wn minus Rn plus Wn Rn. And now we can use the DFT expression. So let's now use x of k equal to summation n from 0 to n minus 1, x of n, w of n, kn. And now I plug in the value of xn, so that's n from 0 to n minus 1, 1/2 w of n minus Rn plus w of n Rn times w of n kn. And so 1/2 comes out, and I'm going to now just write the two summations separately. It's n from 0 to n minus 1. Since these are exponents, I just get minus r minus k n plus summation of n from 0 to n minus 1 wn of r plus k times n. Okay, so I've just combined the two exponentials together, and so now we have to compute these two sums. Okay, and this is again the same thing that we did earlier. This is effectively in the form of n from 0 to n minus 1 r to the n. Okay, so let's call it r1 to the n, and this is in the form of n from 0 to n minus 1 r2 of n. In other words, both of these summations are again just geometric sums, right? Where r1 is equal to wn minus r minus k, and r2 equals to wn r plus k. Now we can compute the geometric sum modulo what we should be careful about, which is that geometric sum formula applies as long as r1 is not equal to 1 and r2 is not equal to 1. If for the case where they are 1, we have to compute the sum manually. Right? Okay. And of course, in that case, it's really trivial to compute the sum because you are just adding 1 n times. So when is R1? So let's first get that case out of the way. When is R1 equal to 1? Now this question that we are asking, remember we are looking at x of k. K goes from 0 to n minus 1, right? R is a fixed number. K is what is varying. So when is R1 equal to 1? We are asking this question, i.e. for what values of k R1 equals to 1. So when is R1 equal to 1 for k in this range? So when k equals to R or R1, no, I guess R. There are too many R's here. K equals to R. So when k equals R, this implies that R1 is going to be Wn to the 0, which is 1. We can ask the same case, when is R2 equals to 1? And that is when k equals to minus R. Right? So when k equals to minus R, so for k equals to minus R, R2 will be equal to Wn R minus R, which is equal to 1. So both these summations, this summation we can compute using geometric sum, except when R1, when k equal to R, we have to manually compute that. Similarly, this summation we can compute using geometric sum, except when k equal to minus R, right? Now, let's look at this. There is this additional factor, which is that we are looking at k between 0 and n minus 1. Right? So when we said that k equal to r, and if you go back to the condition on r, which is that r is between 0 and n minus 1, when you look at this condition, it indeed belongs to this range. So this is a fine condition. What about k equal to minus r condition? Does k equal to minus r fall in the 0 to n minus 1 range? No, because r is itself a positive number. So k equal to minus r is not in the right range. Okay? But there is another number, and that is due to the periodicity of complex exponentials. There is another number which also makes r2 equal to 1. Okay. Remember, we talked about the modulo operation about k, right? We talked about the modulo operation at k. So what is x minus r equal to for something in the range which is positive? So earlier we defined that x minus r is equal to x minus r mod n. Okay, and r is a number between 0 and n minus 1. So if you use the mod formula that I told you earlier, that is also equal to x of n minus r. Right? It's capital N minus the remainder of absolute value of r divided by n, which will be r. So you can indeed verify it also that if you put in k, if we put k equal to n minus r, then r2 will also be 1. And that is the right k that we need to work with. So this doesn't work, but for k equal to n minus r, r2 is going to be wn r minus n minus r, which is going to be equal to wn times n, okay, which is equal to e to the minus j 2 pi n times n. So it's e to the minus j 2 pi, which is equal to 1. Okay. So indeed, for k equal to n minus r, you still get the number to be r2 to be 1. Okay. So we have now gotten those two cases out of the way. So let me write it down below for, so our formula that we had written was x of k equals to 1/2 summation n from 0 to n minus 1 r1 to the n plus summation n from 0 to n minus 1 r2 to the n. Okay. And we are now trying to compute these two sums individually. So let's look at n from 0 to n minus 1 r1 to the n. We said that for k equal to, so for k equal to r, we cannot use the geometric sum formula. So in that case, though, we know that r1 is 1, so we are just adding n numbers. So that is equal to capital N. Okay. Now, for k not equal to r, and k still in the range 0 to n minus 1, we'll now use the geometric sum formula, which is 1 minus r1 to the n over 1 minus r1. Okay. And if I compute that, so I'm now writing only this part. So that is 1 minus r1 is, we had defined it here, it's wn minus r minus k. So wn minus r minus k to the capital N over 1 minus wn minus r minus k. Okay. Now we know that the denominator is of course not 0, so that is fine. Let's look at the numerator. Okay. So this is 1 minus e to the j 2 pi r minus k r minus k over capital N times capital N. Okay. So this capital N cancels. I'm going to keep the denominator as it is. So the numerator is 1 minus e to the j 2 pi r minus k. R is an integer, k is an integer. So what is r minus k? That is an integer, right? So if I have e to the j 2 pi times an integer, what is that equal to? So this is always equal to 1, which means that the numerator is 1 minus 1, that is equal to 0. 0 divided by whatever we have, it's 0. So this means that this first sum is equal to n for k equal to r and 0 otherwise. Okay? So let's look at the second summation then. The second summation is summation n from 0 to n minus 1 r2 to the n. Again, the case where we are going to be dividing 0 by 0, we have to handle separately. So we know that r2 is equal to 1 for k equal to n minus r. So in that case, we just compute the sum itself. So for k equal to n minus r, this is just summation of 1 n times, so we get back n. Now for the other case, we just use the geometric sum formula, 1 minus r2 to the n over 1 minus r2 for k not equal to n minus r. Okay, so let's compute this geometric formula. So R2 is Wn. If we go back, it is defined here. Wn, sorry, here Wn R plus K. So we do that thing. Wn R plus K to the capital N over 1 minus Wn R plus K. We have already gotten rid of the division by 0 case, right? So now let's look at the numerator then. It's e to the minus j 2 pi over n r plus k over n divided by 1 minus Wn r plus k. So n gets cancelled, and what we have in the numerator is 1 minus e to the minus j 2 pi times r plus k. R is an integer again, and k is an integer, so r plus k is an integer. So we have e to the minus j 2 pi times an integer. Again, if I just use Euler's identity, that will be cosine of minus 2 pi times integer, whatever the value of integer is, plus j sine of minus 2 pi times integer. And we know that any multiple of 2 pi, sine is 0, and any multiple of 2 pi, positive or negative multiple doesn't matter, cosine is 1. So this whole thing is 0. So this whole sum is 0 divided by 1 minus wn r plus k, which is equal to 0. So it turns out that the second sum is n for k equal to n minus r and 0 otherwise. Right? So if I combine the two sums then together, what I get is that for cosine, remember we had started with looking at x of n equal to cosine of 2 pi r over n times n over one period. So the x of k we are getting is, if you now add the two sums, it ends up being that it is n by 2. Why n by 2? We got n everywhere, and then there is this 1/2 factor that we had obtained earlier. So it's n by 2 for k equal to r and k equal to n minus r. And it's 0 otherwise. So what we see is that, let's say that r is a number less than n by 2. If I make that assumption, then what I will get is my DFT for k equal to 0, it is 0. It stays 0, and then it is a spike of n by 2 at k equal to r. And then it stays 0, and then there is another spike of n by 2 at n minus r. And then it stays 0 till n minus 1. Again, you notice something similar in this DFT plot, which we'll discuss later. Of course, the difference is that you are looking at only one period of a periodic cosine. But if you ignore that factor and you compare what is the DTFT of a cosine, what is the DTFT of a cosine? You get two impulses. But those two impulses are direct deltas. They are continuous time impulses, right? They are continuous time impulses. You get something similar for DFT. The shape is similar. The x-axis, though, is given by integer values, right? And you are getting two Kronecker deltas, two discrete impulses. So there are some differences, but and of course you looked at only one period. So there are differences, but you sort of get, oh, somehow DFT is related to DTFT, which we'll study, of course, eventually. So these are a few examples to give you the mechanics of how do you compute DFTs and inverse DFTs. Geometric sum, one of the most important things to keep in mind. But while you do that, make sure you don't divide 0 by 0. Remember the Euler's identity. Remember basic facts of e to the j 2 pi times the integer multiple, that's 1, and so forth. And you should be pretty fine doing DFT calculation. Okay, so having computed a discrete Fourier transform by hand, let's look at it in terms of computing the discrete Fourier transform inside a computer. Because as we talked about, the motivation for DFT is that we want our signals, we want a transform that can be computed inside digital systems. So to remind you again, given a signal xn of length n. The discrete Fourier transform formula is summation n from 0 to n minus 1 x of n e to the minus j 2 pi k over capital N times little n. So inside a computer, if you are, for example, programming it in MATLAB, using this computation is very simple in MATLAB. You get a sequence, you multiply it with this exponential, and you add them all up. So there's one way of computing the DFT is using direct computation. So direct computation of DFT, first of all, they require some number of multiplication and some number of additions. So to ask how many multiplications you need if you're computing DFT, let's first remind yourself that k goes from 0 to n minus 1, right? So for one value of k, how many multiplications do we need to do? So each value of k involves n terms, and each term has is given by multiplication of two numbers, and then there are a total of capital N terms. So you have n times n, which is n squared, complex multiplications. By complex, I mean that you are multiplying complex numbers, which requires more real valued multiplications than one real valued multiplication. So this is the case of multiplications. You can also compute the number of summations or additions that you have to do for each value of k. So each k, you have n terms, right? So that means you are doing n minus 1 additions. Right? If you are adding 2 terms, then you are doing 1 addition. If you add 3 terms, then you add 2 additions. So you have n minus 1 addition, and again there are a total of n indices for which you need to evaluate DFT. So you get n times n minus 1 equal to n squared minus n complex additions. So this is the cost of DFT if you were to do it using directly the formula and implement it in MATLAB. What this means is, so let's just, if you just want to talk about what is called scaling analysis, right? So the total cost, if I say that the cost of doing DFT, nothing else matters. The only thing that matters is how many multiplications and additions you do, and you roughly treat addition and multiplication as having the same amount. It takes the same amount of time. Okay. So if you do that, then you say that you need 2n squared minus n operations if you use the formula directly. Okay. So if I say that I have n equal to 100, right, then that gives me certain number of operations. That's 2 times 100 squared minus 100. And if I double the number, n equal to 200, then the number of operations is n 2 times 200 squared minus 200. Okay. Now, if I ignore this minus factor, what this says is that as the length of my sequence increases, or as the number of points that I want to compute for my DFT increases, the amount of time it will take my computer to generate the result will increase quadratically with that, right? If I were to do a plot of, for example, I plot capital N here and I say what is the amount of time it's going to take, right? Ignoring the minus n factor, it's effectively going to grow like this, right? It's going to have a quadratic expression. It's going to be scaling like n squared, which is really bad as you increase the number of DFT points or the length of your DFT sequence. So this was one of the main reasons. DFT was actually known to engineers for a long, long time. But this was one of the main reasons that digital signal processing didn't come into mainstream, even though DFT was known for a long time, because of the complexity of DFT. Okay? But what happened was that really smart people, it is primarily attributed to two people, Cooley and Tukey, but there are many other variants of that algorithm. They came up with something that they called the fast Fourier transform. Okay. Now, this is a basic mistake that students make, which is that they say fast Fourier transform is another transform. It's actually fast Fourier transform. It refers to a collection of algorithms that can compute the DFT in a very fast fashion. Now you can go and read about how fast Fourier transform performs. It basically uses a strategy of divide and conquer. It keeps on dividing your DFT sequence into 1/2, and then it effectively goes to the bare knuckle 2-point DFT. Now 2-point DFT is very easy to compute, and then it sort of builds up from that. Okay, so one of the key facts to make fast Fourier transform is that you want to operate with capital N that is power of 2. Okay. Which is that N should be some power of 2 to the nu. And the reason for that is, as I said, what it does is, let's say you start with 128, it will divide it into 64 pieces, then it will take each 64 piece, divide it into half, 32, it will take it to 16, keep on going down. So if it's not a power of 2, you can't do that fast operation. Okay? So then what happens if your signal is not, so say we are given xn, which is length 1000, okay, and someone asks you to compute its DFT. So if you want to compute DFT of this, right, one is that you can compute 1000-point DFT. If you try to compute that 1000-point, it will not be as fast as you expect it to be. Okay. Why? Because 1000 is not a power of 2. So what you want to do is, if you are given a number, you want to increase the length of your sequence by doing zero padding, adding zeros so that the length of the sequence becomes a power of 2. So in this case, you want to add 24 more elements. You want to zero pad it by 24 zeros to make it 1024. So you want to make compute actually a 1024 DFT. And now it will be fast. So fast Fourier transform, it's abbreviated as FFT. People use DFT and FFT interchangeably. In reality, they are not interchangeable. DFT is the transform, and FFT is the algorithm that helps you compute that transform in a very fast fashion. Okay? Now, how fast? Typically, it's said that FFT has complexity, and complexity means number of operations, has complexity of, so this notation order means I'm ignoring constants. It's n log n to the base 2. So instead of having n squared, you have n log n. So the way to think of this is that direct computation increasing n by a factor of 10. So let's say you originally had some value, you now increase it by a factor of 10. Direct computation means that you will have to wait 100 times longer because the relationship is square. 100 times longer we'll have to wait. Whereas for FFT, if we increase n by a factor of 10, the amount of time we'll have to wait will be 10 times log of 10 to the log of 10n to the base 2. Right? And this log factor, as you know, log is much, much slower than a linear function. So this growth is much slower, right? And in general, you can say that probably you will have to wait, you have increased the length by a factor of 10, you will probably have to wait by a factor of, let's say, 12. You can do the exact calculations to find out what's the factor that you will have to wait. But it will nowhere near 100. And so this FFT, or when people say FFT, actually there is a class of algorithms. MATLAB implements one particular variant of FFT. There is FFT by doing what's called decimation in time, there is decimation in frequency, and all the other variants. We are not going to study them, but this is something that you should be very comfortable and familiar with. In MATLAB, if you want to compute DFT using FFT, the command is FFT. And if you focus on the definition of DFT and inverse DFT, you realize that they are very similar to each other. So actually the similar kind of procedure works for inverse, and so on the inverse side also, in MATLAB it's called IFFT for inverse DFT. Okay. But the main thing to remember is try to use n that is a power of 2.